Ozzy, I've been expecting you. Come on in. You said on the phone you've got questions about my lecture on spectroscopy and quantization of energy levels. Sit down. Yeah, thanks, Prof. Well, I've just got one question really, Prof, but it's a big one. I kind of get the idea of quantization, that the energy of electrons in molecules can only have particular values, and that electron can only absorb exactly that amount of energy that will take it between allowed energy levels. And so it can only particular wavelengths or frequencies of white light can interact with the electrons in the molecules. But I don't know what it means that a wave has energy. I can't visualize what it means for a wave to have energy. I can imagine a moving particle having energy because it's got mass and it's got velocity. And I understand that the waves in the ocean have got energy. But they're vibrations of a substance, and those waves can do work. As a result of particles doing work on another particle, say, their own energy will decrease by the amount of work they'll do. That all makes sense. But do light waves have substance? I can't imagine that. So how can they have energy? Wow. Ozzy, you're asking the very questions that scientists have been arguing about for centuries. So no wonder you have similar questions. I'll tell you about our current understanding. But first, I'll warn you in advance that the nature of light is very complex and, to us, even mysterious. It seems to be something that we've got no experience of in our macro world, in the sense of things to compare it with. So it's okay, and even for the greatest of scientists, it's okay for us to be in two minds about what light is. I'll be more specific about the two minds shortly, but we refer to the dual nature of light, as I said in the lecture. I'll write that on the board. Fortunately, I've already got it there. I don't get it, Prof. You telling me that light can be two sorts of things? It can be two sorts of things at the same time? Or that it can be either of two sorts of things and switching from one to the other? When? If so, if it does switch, when does it switch? Why? Well, no, I don't want to give that impression at all, Ozzy. That's why I wrote dual nature in quotation marks. Although this is the term that scientists use, I want to make it clear that's not what it means. Rather, some of the behaviours of light we can explain, even quantitatively, by presuming that light consists of waves. And some of light's behaviours we can only make sense of by thinking of it as particles. But, listen up here, Ozzy, I am not saying that light is either a wave or a particle. I'm not saying that it's both a wave and a particle. I'm not saying that it switches between being a wave and being a particle. Rather, it's something beyond our comprehension. But we can explain some phenomena by using the theory of waves and other phenomena by considering a wave to be a particle. You mean that scientists don't actually understand what light is? How am I supposed to? I've got an exam next week. You're absolutely right, Ozzy. Nobody understands the true nature of light. But some phenomena we can mathematically describe and predict with remarkable precision using the theory of waves. And some phenomena we can mathematically describe and predict very, very precisely if we consider light to consist of particles. So you see, there is a duality, but the duality is not in the nature of light. Light is what it is, something we don't quite understand. The duality is in us. We have to switch from one way of thinking about what light is to another way, according to the circumstances. We have the duality. Well, I'm flabbergasted. I can't believe that scientists don't actually understand what light waves are. I understand your grief, Ozzy, but there are lots more examples. One common example is chemical bonds. Scientists use a whole raft of different models about bonding, each model to best explain different properties of substances. But that's a digression. In your physics classes, I imagine you've learned about reflection of light, refraction, diffraction through slits, and interference patterns. Good. So to explain those behaviours, you probably used a theory of light as a wave developed by a scientist called Huygens, Huygens. He proposed this wave model of light way back in the 1600s. So we're talking 400 years ago. But around about the same time, the genius that we know as Isaac Newton, who was both a mathematician and a scientist, argued that light was composed of particles. As it turns out, for many, many decades, a couple of centuries in fact, the wave model dominated. Until about 100 and a bit years ago, the phenomenon of the photoelectric effect was observed. Now, we're not going to go into this, I'll leave that for another day, but this is when you shine ultraviolet light onto some surfaces and electrons are ejected. Now, that gives rise to arguments that the radiation, ultraviolet light, and then visible light consist of particles. We can't attribute all the progress to one person, but we attribute an awful lot to Albert Einstein, a name that you would be familiar with, who concluded that this photoelectric effect could only be explained by considering light to consist of particles. And he proposed that the light consists of small packets of energy, which we now call photons. The real cruncher came with the work of an American physicist by the name of Compton, Arthur Compton. He made measurements on the interaction between light and electrons, and he showed that if electrons were set in motion by the action of a light ray, it behaved exactly as if it had been struck by a pulse, a short, sharp pulse of energy, corresponding exactly the way that Einstein could calculate the energy of photons from the wavelengths and frequencies of light waves. So the evidence was that the light was a pulse rather than a continuing waveform. So even though we don't understand what light waves are, can we actually calculate the energy of these photons? Yes, we can, and it turns out to be quite a simple process. Einstein concluded that the energy of a photon, if we think of light as a photon, is proportional to the frequency of the wave, if we think of light as a wave. Try and accommodate that. And more specifically, that the energy of the photon, the proportionality constant h, the energy of the photon, frequency of the wave, and h is called Planck's constant. the value of which is 6. I've got some notes here. 6.626 by 10 to the minus 34 units of joules seconds. So let's take, for example, a light ray of red light, wavelength in a range. We'll just take specifically 700 nanometers. Oops, yep, that's correct. Which is 7.00 by 10 to the minus 7 meters. And the speed of light we know to be 3.00 times 10 to the 8 meters per second. So the frequency, the number of waves per second, has to be the speed of light by how far it is between each, the length of each of the waves. And that's c on lambda. Simply divide that by that. And we'll finish up with, if my notes are right, 4.29 by 10 to the 14 per second. It's making 4 by 10 to the 14 vibrations per second as it travels at this speed. Just by the by, this unit is now, the standard unit is same number, same thing, but it's called Hertz, Hz. Right? So now the energy of the photon h nu is 6.626 times 10 to the that should have been minus 34, I'm sorry, minus 34 times 4.29 by 10 to the 14, and I get my units in right, the seconds and the per seconds cancel out, and I finish up with 2.84 by 10 to the minus 19 of a joule. Quite simple calculation. Now that's not very much energy, but that's one photon. And if you took a mole of photons, 6 by 10 to the 23 of those, each with that amount of energy, would have enough energy to raise the temperature of 1 litre of water by about 40, 41, 42 degrees. So yeah, that's significant. Most importantly, if the energy gap between allowed levels of an electron in a molecule are the same as that, then these photons will be absorbed. And if it's different from that, if the energy gap is different from that, then photons with the corresponding energy will be absorbed and excite the energy to a higher level. So if it helps you to, if you want to think about light waves as being particles, go for it. Feel free to do so, because that's one of the ways that scientists resort to make sense about what waves are. Go for it. Aha. So the chapter heading in our book is the dual nature of light. But light doesn't have a dual nature. Light is what it is. So the title should be Light, the dual nature of scientists' explanations. Is that right? With no need for quotation marks, because that duality is a reality. That really is a duality. You're right. I'll change the heading. Thank you.